Okay, welcome everyone to this morning's session. And to start with, we have Richard Wentworth, who gives some remarks on Yang-Mills type equations in higher dimensions.
Thank you, sir. So, along with the other speakers, I would like to thank Luis and Tomas. Where are they? There you are. For putting on this conference despite lots of adversity, and it's a great pleasure to be here to celebrate the career of Oscar García-Prada. I think we met at the Durham conference for the first time, that famous Durham conference in '93, and I learned a lot from Oscar at that time. But we've been continuing to have fun together and be in contact with each other for over the years. At Steve's 60th birthday conference, Oscar had a wonderful collection of photos, and it reminded me of a trip that we took. We made a hike up to the top of Angel's Landing in Zion National Park, and it was clearly a trip that we all remember and really enjoyed. So I think of that time very often. So, okay, so I would like to so also Steve in his exposition of all the things you've been interested in over your career made it clear that the Hitchin-Kobayashi correspondence in particular has played a big role in a lot of things that you've done. And of course, this is a really powerful idea that's been around for a long time, but nevertheless continues to produce interesting results. And so I would like to talk about today. One part of it, anyway, is a generalization of this. Believe it or not, another kind of Hitchin-Kobayashi correspondence. So let me begin by recalling Miałka's formulation of the Bogomolov-Giesecke inequality. So let's let X be a normal projective variety. Save dimension n. And I'm going to assume that the singularities have codimension at least 3. Okay, and then let's choose ample divisors. N minus 1 ample divisors on X. Let's choose a coherent sheaf on X, so reflexive. Coherent sheaf. Say of rank R.
This is the same n?
Yeah, it's the same n. I'm choosing n minus 1 different divisors. Yeah. And so let's define the degree then of E as the intersection of the first term class with these divisors. And then once you have the degree, you can define the normalized and degree as usual. R, which is the rank of E. And then you could define a notion of stability. So E is stable if F is strictly less for all proper saturated subsheaves. F of B. Okay, and so then the theorem of Miałka. I think this is like 87 or something, is that if E is stable, then 2r times C2 minus r minus 1, C1 squared. Okay, I understand now. This is going to be tricky. Intersected with any combination of these where you admit one of the divisors is always non-negative. So for any I. Okay. No, n minus 1. So I just omit one of them. This means I omit only hi. Okay. All right. So this is a very nice theorem, and so the goal is to give an analytic proof. Of this inequality, which I'll call star. Yes. For example, if you could take them all to be equal, sure. This is, yes, it's related to the cone of movable curves. In fact, yeah, indeed. But I'm not going to really, that's not going to be important for me, but you're absolutely right. Yeah. Okay, so you might ask why, right? Why do we want a different proof, an analytic proof? Now, okay, I'm among friends here, and I'm sure you wouldn't ask me that question, but you could ask that question, right? So why do you want such a thing? So let me try to give a couple answers anyway. So one reason might be that you might want to move outside the world of algebraic geometry. So you could try to generalize this to Kähler varieties, for example. If you have an analytic proof, normally the algebraic aspect is not as important, so you might be able to generalize things to Kähler varieties, for example. So I'm not going to discuss this, but let me just mention that there has been some progress recently in this by Xiaojun Wu and my collaborator, Shumio Chen. So I have to sort of explain what this means in that context. No, I'll discuss what they do. So for the Kähler variety case, I have to sort of, tell you what I mean by this, but one can do that. So, but I'm not going to, because this is not what I want to talk about. Another nice thing about having an analytic proof typically is that it gives you information about the case of equality. Okay, so let me state a theorem then, right off the bat. So this is with Shumio Chen from last year. So if we have equality, then that implies that E is actually locally free on the regular part. It's a vector bundle over the smooth part of my variety, and it's projectively flat. Okay, so I'll sort of indicate the proof of this as we go along. So there are other reasons why you might be interested in this. So you can already see that this is, you see where I'm going. There's going to be some sort of a generalization of the Hitchin-Kobayashi correspondence for not taking a single Kähler form, but a whole bunch of Kähler forms. So this is sometimes called a multipolarization in the literature. Okay, Now, why would you want to look at multipolarizations? Well, sometimes you're interested in how the stability condition changes when you change the polarization. And if I were to take all the H's to be the same, like one normally does, then in higher dimensions, you see that this condition of stability is nonlinear in the polarization. And so, people are interested in wall crossing formulas, but now the wall is very complicated. It's kind of this nonlinear thing. And so there's, this is sort of my third kind of motivation. There's a paradox of Alexander Schmidt that shows how I won't say exactly what this is unless you ask me, but it shows you that this can be very, very strange, this kind of wall crossing phenomenon, if you use a single polarization. But if you use multipolarization, then you can vary these individually, and now you can expect kind of a nice wall crossing formula. And so this has been sort of pursued by Daniel Greb and Mate Toma, and some other work of Greb, Ross, and Toma. And in particular, they construct projective moduli spaces of slope stable sheaves. Even in this multipolarization kind of situation. So that's kind of why multipolarizations are interesting, I think. Now, how about for generalizing to singular varieties? That might be something that is very natural to do. The motivation actually for us was to try to give an analytic proof of the Mehta-Ramanathan restriction theorem. Now this, maybe I don't have to justify, this would be kind of interesting if one had a nice analytic proof that in fact, Miałka used that to prove this theorem to begin with. So we weren't completely successful here, but if I have time, I can tell you a little bit about what we did. But anyway, the generalization to singular varieties really comes from looking at this. All right, so that's kind of my introduction and motivation. So I'd like to just give you some background first, and then I'll divide up the talk into two parts. One is to understand how this multipolarization works, and the other one, how to do things on singular varieties. Okay, let's see, great. All right, just some background that most people probably know here. So very, very classically, so if X is smooth and E is a vector bundle, then of course we have the Donaldson-Beck-Yau theorem, which says that there exists a Hermitian-Einstein metric. Okay, and with the Hermitian-Einstein metric, so that's a particular condition on a certain part of the curvature, and it's just enough to derive the inequality. So from here, you can derive the Bogomolov-Giesecke inequality. Maybe I should just restate it here in sort of a more differential geometric form. It's just now you can integrate the same quantity, C2 of E, thinking of these now as cohomology classes against a Kähler form or single I should have said that. So X smooth here, let's say projective, but it could even be paler. Yeah, of course. Yeah, E is that's what I'm going to assume throughout. Now, with respect to this single Kähler form, and this is just a restatement of the inequality in the sort of cohomological formulation. And sorry, and -2, thank you. And so then the idea is, of course, how to get this, the inequality is to use Chern-Bay theory, of course. Namely, these Chern classes are represented by, again, I'm sorry to emphasize this, but you'll see that it's important, is represented by Chern-Bay forms, depending upon this Hermitian-Einstein metric. And now, if you play around with the conditions of Hermitian-Einstein condition, then you can derive this inequality, which I think was first done by Lübke. Not sure about the history here. And also the case of equality. All right, so that's ancient history. So then this was generalized, still in the case where X is smooth, but where we allow for more general sheaves by Bandov's. So this is around 91. So here, X is still smooth. Should have said compact Kähler, of course. That's important. Smooth compact Kähler. But where I allow now E to be just a reflexive sheaf, or even torsion free, but it's just reflexive. So then they make a key definition. Okay, so here's the key definition. So a metric, a Hermitian metric, H on the smooth part of this, where the place where it's a vector bundle, is called admissible. If the curvature of the Chern connection, where this guy is in L2, and the Hermitian-Einstein tensor, so the contraction of the curvature with the Kähler form, is in L infinity. Okay, so it might not be so obvious where this condition comes from. L2, maybe you think of Yang-Mills, and that's based on the L2 norm of the curvature, so that kind of makes sense. But this condition is a very natural one as well. After all, we're trying to solve the Hermitian-Einstein equation where this says that this is a constant, and so that's a very natural condition. Okay, and so their theorem, let me state it in a multi-part form. So this is about Sue. Is first of all that these metrics always exist. That's not completely obvious. So admissible metrics always exist. No condition at all. And then assuming stability, oh, I should say something as well here. Yeah, okay, so then we have the analog of the Donaldson and Beck-Yao theorem. So assuming stability, we have the existence of an admissible Hermitian-Einstein metric. Let me get these right. And this is what I wanted to say. The other thing that is true is that the Chern-Bay forms define closed currents that indeed represent churn 1 of E and churn 2 in cohomology. Okay, that's very important because, of course, we want to use that to deduce the Bogomolov inequality, and it comes via churn waveform. So we better make sure we're talking about the actual churn classes. So in particular, this gives you the inequality in this case as well, and the statement about equality.
Can you just say something about the squareability of churn 1?
Yeah, it's the same thing. So again, this involves the square of the curvature. It's an L2, so that makes sense at least as a current. And then to really prove that they're closed, we use a result from your thesis, actually, a very nice way of showing that these things are closed. So, okay. Now let me just say one more thing about Bandeau and Su because it will come up later. They prove an extension theorem, which is really important. It looks technical, but it's extremely important. So they also prove an extension theorem. I guess I'm down to 4 here. So this is kind of related, but let me just state it in a way that is somewhat separate. So let's let S be a closed set of Hausdorff codimension 4. And we could do this on non-compact. It's important to do this on non-compact as well. So so this is finite Hausdorff codimension 4 dimension measure, and suppose that E is a vector bundle, holomorphic vector bundle, with the metric H such that the curvature of the churn connection is in L2. Okay. Then E extends uniquely as a coherent sheaf. So E extends uniquely as a coherent reflexive sheaf. Okay. So we don't need this condition at all, just L2 of curvature is enough. Okay, so it's a very, very strong theorem. And there's another part that's equally important, and that's that, moreover, local holomorphic sections. So I'll denote the extension by the same thing. The are locally bounded. So as I say, so since I don't know how I'm going to do with time, let me just tell you why this is so important. Even when we get to the very general case, or even here, well, I guess here maybe we can avoid it, but certainly when we allow X to be singular, even proving the so-called easy direction of the DUI theorem, namely assuming the existence of Hermitian-Einstein metric, you want to prove stability or Pauli stability, even the easy direction is not obvious. And it depends a lot on this kind of regularity of local holomorphic sections. So as I say, maybe I'll say more about that later, but we'll see. Okay, so that was sort of the state of things for a long time. And so now we sort of have two tasks. So our tasks R1 to generalize to the multipolarization case. And it turns out that this is embarrassingly easy. There's not much work involved here. And then the other one is to singular varieties. Okay, so let me just treat these separately. So maybe 1 and 2. Okay, so to prove 1, we just have to make a definition. So so there's a more general statement here, but let me just make the definition for the case at hand. Okay, so Hodge-Riemann form. So first of all, this is just going to be for pointwise, so for constant forms on Cn. So let's let omega be a positive 1,1 form. Yes.
The Hermitian metric only defined in the complement of S.
Yes, it's only defined on the complement of S, exactly. Now, the result of this theorem here, if you assume a little bit more admissibility in this sense, then you can extend that metric in a certain Sobolev space to the smooth part of this reflexive sheaf that gets extended. So the singularities of a reflexive sheaf live in codimension 3. This thing is codimension 2. So we extend the sheaf, and so it's going to actually be locally free. It's going to be a vector bundle on a part of S. And so there you can show that the metric has some regularity. Okay. Under this additional assumption of admissibility. And of course, if it's Hermitian-Einstein, then it's smooth there. But you do get a little bit more regularity. Okay. So again, these are just here. This is just constant forms for the moment on Cn. So I'm going to choose a positive 1,1 form and omega any n-2 n-2 form. Okay, you can generalize this omega here, but let me just do the n-2 n-2. And then we construct two things. One, the primitive classes. So PQ. So these are the set of all alpha that wedge trivially with omega, wedge omega. And then a bilinear form. So square root of -1 to the power p minus q. Sorry about this, but and then star of alpha wedge. So this is the bilinear form. Sorry, alpha bar. What am I doing? Sorry, beta bar with omega. Okay. So this is a bilinear form on forms of the right dimension. So here, what are P and Q? So P and Q are any positive integers that add up to 2. So since I'm in this very special case, there aren't a whole lot of cases, right? Either you're looking at 1,1 forms or 2,0,02 forms. So, but you can generalize this notion and this definition as well. But for us, this is enough. And so let me make the definition then. So we'll say that so we'll say that omega is Hodge-Riemann with respect to little omega if two things hold. One, there's an orthogonal splitting. So in this case, it's just on the 1-1 part. In general, there will be more places in terms of primitive things and then multiples of omega 0. And then the second condition is that Q is positive definite on primitive forms. On primitive forms. Okay, so this is a generalization of the usual Hodge-Riemann. So the classical case is when omega is little omega to the power n minus 2. Okay, then this is the input for the Hodge-Riemann bilinear relations. And so there's a theorem. It's not so old. Of T-Moduli from 98. And this is sort of after some partial result of Gromov in a preprint that says that if I choose omega 1 to omega n minus 2 positive 1-1 forms, any positive 1-1 forms, then setting omega equal to this wedge product is automatically Hodge-Riemann with respect to another one. It's a very, very general kind of result. And let me just say, in this case, there exists a positive 1-1 form omega such that this omega is, omega wedge, this guy is, say, omega to the n minus 1. Okay, so this is a kind of a linear algebra result, really, but not a trivial one by any means. But it sort of allows us to make a definition. So now let's go to a complex manifold. So here's our definition. Let's let omega 0 be a positive 1-1 form on a complex manifold X, and omega is any n minus 2 form. So we call the pair a Hodge-Riemann pair if, of course, omega is just pointwise Hodge-Riemann with respect to omega 0. And 2, I want omega to be closed, and omega wedge omega are both closed. Okay. And so we add the closed condition. And so this looks like a very, very restrictive condition, and of course it is, but there are plenty of examples. So because of Timoran's theorem, for example, I can take omega to be the product of n minus 2, say, Kähler forms. And if omega 0 is also scalar, then this condition also is trivially satisfied. But you can see that there are plenty of other examples where you might imagine that that you don't have to have omega 0 to be scalar. You don't have to have these forms to be scalar where these two conditions are satisfied. Unfortunately, I don't know any examples. We looked pretty hard, but
By this theorem that you mentioned, theory, all these manifolds are automatically balanced, right? Either.
exactly. So this condition means that there's a balance, that this Hermitian metric is balanced. So this guy, even if all of the omega, that's a very good point, thanks. Even if omega, in this case, where omega 0, omega 1 through omega n minus 2 are all scalar, this guy is not. All we know is that it's balanced, indeed. Okay. All right, so so then the theorem is the following. So why did I really, I mean, this is sort of the minimal thing you could do, because first of all, I want to define a notion of stability. So this really better be closed, or at least DD bar closed, but let's say closed. And then for the Bogomolov-Giesecke inequality, we're going to use this one. And so that one should also be closed. So these are sort of minimal conditions in order to even state a theorem. And so here's the theorem, but it's really an observation. Okay, so this is it's almost embarrassing to call this a theorem, but because we're just using kind of known results in some sense. So let's let omega 0, omega be a Hodge-Riemann pair. Again, I don't know whether this implies X is scalar or not. I actually don't know. Okay. Define stability of sheaves by using the degree of E to be the integral of C1 with omega 0 and omega. And that makes sense because we're assuming that this is closed. And then the statement is that if E is polystable, so then E is polystable. Sorry, yeah, again, a reflexive sheaf. Yeah. So E is polystable if and only if there exists a Hermitian metric. So admissible, maybe. If it's a sheaf, admissible Hermitian metric, satisfying kind of the Hermitian-Einstein condition, but let me write it like this. So the Chern, the curvature of the Chern connection, wedge omega 0, wedge omega is equal to some multiple times the identity times, say, omega squared. And this constant. Okay. So, so again, this is kind of a kind of a generalization then of the Hitchin-Kobayashi correspondence to these guys. And the particular case that we're interested in is exactly this one, right? So this can be applied to the multipolarization case. And so the Bogomolov-Giesecke inequality. Yes, thank you. I'm definitely assuming X is compact. Exactly. Okay. So then there's a moreover here, and the moreover is the Bogomolov-Giesecke inequality with respect to omega. Let's get this right. Okay. With equality, if and only if E is locally free and projectively flat. Okay, so that's in particular, at least when X is smooth, this gives a proof, an analytic proof of Mianca's inequality, because we can apply it to the case where we're just taking wedge products of Kähler forms.
You know, if one can reverse the images, it can have a complex manifold compact with that management. Can I find what
I think that's false. I can't remember now why, but I think that's false, actually. I think that I'm sorry, I just am blanking a little bit. I can't remember now what we did think about this, but I'm pretty sure that's not true. So somehow this is so balanced, of course, is a pretty strong condition. This is even stronger, I think. But as I say, there are lots of examples. Okay, so then there's another theorem which is maybe a little bit more interesting, and that's the non-abelian Hodge correspondence. So we can generalize Carlos's result here, and let me formulate this. So there's a one-to-one correspondence between. So on the one hand, rank R, semi-simple flat bundles on X, and polystable rank R Higgs bundles satisfying the condition. Now we use these two forms, right? So churn one with these two classes. So churn one has to be 0, and churn two with omega has to be 0. And again, the proof is kind of just using the proof that Carlos gave, because what he really used was the Hodge bilinear relations. So this is this is fine. This is slightly remarkable because, as I say, the underlying metric here that I've erased that we're using on the manifold is just a balanced metric. And Indranil, so this was, showed that non-abelian Hodge does not hold in general. For Godeschomp metrics. So my guess is that it doesn't hold for balanced metrics either, but it does hold for these things. That's kind of why I think that this is even stronger than the balance condition. But I don't know that, I don't have a proof of that statement, but that's kind of what I think is going on. Okay, so, right, how am I doing on time? Oh, not very good at all. Yeah. Any questions? Okay, so as I say, that takes care of kind of the multipolarization aspect of this problem. So, I'm not sure how much I'm going to be able to say about the more interesting problem, actually, namely how to generalize Donaldson and Bacchiao on normal varieties. So let me just set up the situation again. So this is going to be a normal variety. Dimension n, I'm assuming that the codimension of the singular set is at least 3. And I'm also assuming that I'm using the Kähler form, which is just the restriction of a smooth Kähler form on a smooth manifold. So this also is kind of important, which I think this condition can be removed by the work of these other guys that I mentioned before. So let me just state the theorem then. So this is, so this is from last year again. So a reflexive sheaf E on X is omega polystable if and only if E admits an admissible Hermitian-Einstein metric. And this metric is unique up to a constant, in case you were wondering. So admissible is defined in exactly the same way. Again, it's going to be a metric on the smooth part of E over the smooth part of X. Okay, again, with the same conditions, L2 curvature and bounded Hermitian-Einstein tensor. Okay, so this is the generalization to normal varieties, projective varieties. Okay, so I don't have a lot of time, but let me just kind of say a few remarks here. Maybe the one that's slightly more interesting than the actual details of the proof are how to define things. Oh, and I should have said that the theorem that I stated in the beginning, of course, the Bogomolov-Giesecke inequality and the statement about equality kind of uses this theorem, kind of with a little bit more work, but that's the heart of it. Okay, so the first thing to. Okay, I have 2 more minutes than what the clock on the wall says, which means no, I have 2 minutes. Yeah, okay. All right, so let me just say one aspect of this that I think is maybe the more interesting thing. The first thing you confront is that on general and singular varieties and coherent sheaves, Chern classes are in homology instead of cohomology. Right. So in general, Chern classes are in the child group, or let's say homology. Not cohomology in general. And so you might even wonder, what's going on with Chern-Weil theory and how do we apply these things? So let me just say one thing. So because the codimension of the singular set is at least 3, there's a homomorphism from H2n minus 2i of X to the dual of compactly supported forms on the regular part. For I equals 0, 1, and 2. And on the other hand, given an admissible metric, H on E, then Chern 1, well, Chern 0 is clear, but Chern 1 and Chern 2 define closed currents on compactly supported forms. So this is maybe the difference from the other case. We don't know. In fact, it's probably not true that that they define closed currents on all of the forms on whatever we mean, and then on the cohomology of X, but at least on the compactly supported forms they do. Okay, by the same argument that we had in the smooth case. And so there's a little proposition that sort of gets everything rolling is that regarded as elements of that space, churn one, well, churn I for I equals 0, 1, and 2 represent the image of the actual churn classes. Okay, so this is necessary because, of course, once we have a Hermitian-Einstein metric to get the Bogomolov-Giesinger inequality, we still have to apply churn-Bay theory, and this is what we mean by churn-Bay theory. And this is good enough to give it. So I think I'm out of time. I'm definitely out of time, so I'll stop there. Thanks.
Are there any questions or comments?
I didn't plant this one.
In the usual situation, Donaldson-Uhlenbeck-Yau, the Hermitian-Einstein appears as a moment map equation.
Right.
Can you use this big omega and omega 0 to define the symplectic form on the space of connections so that
that's a good idea.
that actually appears as a moment map equation as well?
That's a good idea. I haven't thought of that. Yeah, I haven't thought of that. I don't know the answer to that question.
So also in the non-abelian Hodge, there is the proof of existence of harmonic metrics, right?
Yeah, exactly.
And so the fact that it's not Kähler is not important from
That's
that
right.
point of view, right?
That's
So we
right. But to
can-
prove plurisubharmonicity,
That is,
that's what fails in the Godesholm case, apparently.
yeah, I see.
And that's exactly where we use this extra condition.
Okay.
And that's what you need for that Hodge correspondence.
To work for the also the
to get the
existence
Higgs
of harmonic.
So
of harmonic
exactly
matrix.
where it fails is going from the harmonic map to the Higgs model.
Okay, I see. Okay, great.
Maybe I had one question from the, didn't quite follow from the way you explained this story with the HR pairs, whether you are in the end getting different notions of stability which are new.
They're definitely they're not really new in the sense that it's stability with respect to a balanced metric,
Right, but not
a balanced remission metric. So of
necessarily
course
metric.
that's why I say the proof of the theorem is really just using known results, because we know the existence of Hermitian-Einstein metrics for actually Godesholm metrics. So so in that sense, it's not really new. The main point of introducing all of this stuff was to get Bogomolov-Giesinger, because Bogomolov-Giesinger doesn't even make sense for Godesholm metrics in general. So yeah.
Okay. Thanks very much. Any more questions? If not, let's thank Richard again.
Okay.